Hi, in this video we are going to talk about the concrete implementation of the Sudoku problem. So let's get started. It is going to be familiar because it is basically the same for all the backtracking algorithms, and we have been discussing several backtracking algorithms so far, such as the coloring problem and Queen's problem and so on. It is going to be the same. Here we are going to have a two-dimensional table, the so-called Sudoku table. It's going to store integers. And we represent the Sudoku table with a two-dimensional array. And of course, the 0 represents the empty cells we have to find out for the solution. Okay, so of course we instantiate the Sudoku and we solve it. In the constants, I create first of all the private constructor. Why is it good? Because we can make sure with the help of a private constructor that this class cannot be instantiated, and that's what we are going to do, because it's going to store just single integers, such as the board size, the minimum number. We have been talking about in the theoretical section that we are able to find numbers in a given range, ranging from 1 to 9. So I will have a minimum number, and that's the lower bound of the range, and that's a maximum number, the higher bound of the range. And of course we have the box size, as we have discussed in the theoretical section too. The whole grid contains of 9 boxes, and the size of these boxes are 3 by 3, so it has 3 rows and 3 columns. So that's what I denoted with the box size. It's going to be 3. Okay, so what about a Sudoku? Of course we store a reference to the Sudoku table, and of course we have a solved Sudoku problem. If it's going to return null, it means that we can show the result, and else we can print out the solution. Of course, just to be consistent, we do something like this in the Queen's problem and the coloring problem. So we not check whether it is a good solution, but we look for whether it is not. If it's not a good solution, it means that it's going to return false, so no feasible solutions, and anyways, we just show the results. So the show result is just to iterate through the two-dimensional array, the so-called Sudoku table, of course with some spacing. I'm going to give spaces after each box. So that's why I inserted these modulo operators. So if it's divisible by 3, it means that that's the end of a box. So I print a space and a space there. So it's just a for loop, and of course we just print out the Sudoku table given items with index, row index I and column index j. Okay, what's more important is the so-called solve. Of course it is a boolean, and we have to specify a row index and a column index. So what does it mean? It means that we start from the 0 row index and the 0 column index. So this is the item we are starting. Of course, we wouldn't be able, we would be able to start it from here because we have already specified it. But anyways, I started the 0 index, 0 row index, and 0 column index. If we get to the end of the board, it means that we return true and we have a solution. So it's not going to be false, so this is going to be called. If we get to the end of the board size, we have to set the row index to the 0 because we jump to another column. And we have to reinitialize the row index to 0 because it means that we have already get to the board's edge. And anyways, if the Sudoku table is not 0, it means that we have already inserted some numbers there. So we just have to return false. Not return false, we have to call this method recursively, and of course we have to increment the row index. So the algorithm starts by here and it's goes here. For example, this situation is quite good because we come to the conclusion that it is not 0, and if it's not 0, we call the method recursively, but we have to shift the row index. So we jump to this position. We check whether is it the end of the table. No, so we keep going. So this is false. It's not the end of the table. It is not equal to the board size because it would be the board size. Here it is not. It is not 0. So we call this method. And here we just iterate through from the minimum number to the maximum number. So from 1 to 9. And we try to find the solution, whether it is part of the solution or not. So we check whether 1 is a good solution. No. Then 2 is a good solution. No. And if of course it's not a good solution, we have to backtrack. So we have to check whether it is legal. I'm going to rename it to valid because that's what we have been calling this method for Anquin's problem and so on. And it is basically the same for every backtracking algorithm. So we have to check whether it is a valid move. And what have been we discussing in the theoretical section, that we have to check 3 cases, 3 scenarios. If the given number is already in the row, we know that the number cannot be part of the solution, because that's the first rule in the Sudoku table, that in a given row, every number is distinct. So there is no 2 same number. So how can we do it? We just iterate through, not 9, sorry, but the constant. That's why I created the constant. So board size, and board size, of course, and check whether we have already been using this number. And if it's yes, we have used it, then we return false. It is not a valid position. We iterate through the columns, the given column, and we come to the conclusion that if there's the number we are looking for, it is not a feasible solution, because we would use a same number twice in the same column, and it is forbidden for Sudoku. And we have to check that the given number is a single one in the given box. The box size is 3 by 3. Sorry, I should use constants here. Box size, of course, constants dot box size. So we have to calculate these box row offsets, because it depends on what boxes we are considering. We have a box in the first row, but we have 3 boxes in the first row. We have 3 boxes in the second row and 3 on the third row. So we just calculate that what are the boxes we are considering. And of course we have to iterate through this box. It consists of 9 items, and we have to check whether the actual number is present here. If it's present here, it means that we are not able to reuse this number and we return false. It means that we are going to return false if it's not valid. If it is valid, then we set the given number to the Sudoku table with the row index and column index. So we are going to update it. For example, we come to the conclusion that it is valid to put 10 here, and we are going to update it with 10. And we try to solve it for the next row index. That's why we increment it by 1, and we call this solve recursively. Anyways, we come to the conclusion that we have to backtrack. We have to backtrack. So this is the backtracking. We come to the conclusion that, okay, there is no feasible solutions, so we set back to 0, which means that we can reuse it again. And anyways, we return false, so it means that there is no feasible solution. I'm going to get rid of this. Okay. So basically, these are the most important parts of backtracking for Sudoku. So we have to check whether, and that's the same for Anquin's problem, Hamiltonian cycle. We have to check whether, are we finished yet? And if we finished, yeah, there's a solution. If not, we have to check whether we are able to write numbers to that given position, so that cell is empty. And anyways, we have to check every number from 1 to 9. If it's valid, oh, it is not valid. If it's not valid, we have to backtrack. And of course, the 3 important cases for Sudoku, that we are not able to reuse the same number in the given row, we are not able to reuse the same number in the given column, and we are not able to reuse the same number in the given box. And that's what we are checking here with linear time complexities. We have to iterate through every numbers in the given row, in the given column, and in the given box. So okay, that's all about the implementation. Thanks for watching.